Hello one and all, Jake here, and what you're watching is part 2 of a 2-part series about one geometry problem that frankly shouldn't take 2 videos, but I wanted to make a point out of this, alright? So go watch part 1, it'll put what you're about to see into more context. Alright, so on the top of the board here, you see the same knowns that we had before, right? Those are the 2 things we start out knowing when we started solving the problem. We're going to use these 2 knowns and synthesize some new information that will help us solve the problem from a different direction than we did in part 1. All right. So there are 2 things sort of present in the problem. There's the area of a quadrilateral and there's the area of a triangle. And you could decompose the quadrilateral into just the area of 2 different triangles and therefore technically use less information. But why do that when we can prove something new and then use that instead? So what we're going to do is we're going to draw a quadrilateral on the board, right? If this marker would cooperate. That is the worst quadrilateral ever. Hold on, folks. Okay, that is even worse. All right, so here I have this generic quadrilateral. I don't know that it's a square. I don't know that it's a rectangle. I don't know it's a parallelogram. I don't know it's a rhombus. I don't even know that it's a trapezoid. How on earth can I find its area? I want you to do like a Jimmy Neutron brain blast back to the past. Go back to like 9th grade geometry or maybe like even some middle school geometry. Think, did I ever learn how to just find the area of a quadrilateral just generically? We did for triangle, right? Was there something like that for quadrilateral? The answer is probably not, unless your school district was very different from mine. I never learned a way to just generically find the area of a quadrilateral. In fact, I wouldn't even really know where to begin if I didn't know what I now know. I feel like there are a lot of different ways you can draw a quadrilateral and the area can get all weird. And is there always definitely like a clean way to do it? It doesn't seem obvious that there is, but actually there is one. And I'm going to show you what it is. So let's say we draw a diagonal. We'll call this D1. And then we'll draw the other diagonal too. And we'll call this D2. And then we will find the measure of an angle that these 2 diagonals make with each other in the center of the quadrilateral. We'll call that alpha. That is all we need to know. We need to know D1, we need to know D2, and we need to know alpha. Once we have that, we can find the area of this quadrilateral. I know what you're probably thinking. Wait, D1 and D2 and alpha are all you need? You don't even need to know a single side length to find this area? Yes, that is exactly right, and I'm going to show you how. So, we know the area of a triangle formula right here. So, let's try to split this quadrilateral up into 2 triangles. We already have the diagonals in place. All we need to do is sort of mentally make the connection here. So we'll call this the red top half and the bottom blue half, I guess. Okay. All right, now something else that's worth noting here is that we kind of went over this a little bit, but this opposite angle here also has the same measure alpha. And then if we set, some beta equal to pi minus alpha, well then this angle and this angle both have beta measure. All right, so how would we normally go about finding the area of this red top half triangle? What we would do, using the method we've been using, is we take a base. In this case, we're going to choose the obvious D1 as our base. We know the length of it already, so it's a very normal choice. And we would draw from the opposite vertex down to the line containing the base, and altitude. And then using this altitude, what we would do is we would need to know the length of this little line segment right here. We would multiply that by the sine of alpha because, you know, opposite divided by hypotenuse. That would be our sine of alpha. And then since the sine of alpha is just the length of this altitude we just drew divided by the length of the hypotenuse, which would be this line segment right here in the case of this triangle, we would be able to find the height, and then we just do 1/2 base times height, right? The problem is we don't have the length of this line segment right here. And so let's hold off on that idea for a second. What about the bottom blue half? What would we do? Well, we would do much the same thing. We would take D1 as our base. It's a logical choice. We already know the length of it. And we would take the opposite vertex, draw an altitude down to the other side, and then it would form a right angle. And then in order to find the length of this altitude, we would take the length of this line segment, multiply it by the sine of alpha, and then we get our result. We don't know either of these line segments' lengths, unfortunately. But what we do know is their total length. And so what we can do is, let's just say this corner is A, and then this middle segment we'll call Q, and then this outside one we'll call T. I don't know. All right, so what do we have here? For the figure I've drawn at least, what we would have is area of red is just 1/2 times the length of the base, which is D1, times the height. What is the height? That is QT times the sine of alpha. All right. How about the blue? It's kind of similar. 1/2 times the base, which is also D1. We're using the same base for both. Times AQ times the sine of alpha. Now, our total area that we want to find, we'll call that A total, is A red plus A blue. And that would be 1/2 D1 QT sine alpha plus 1/2 D1 AQ sine alpha. And we can sort of combine like terms here, distributed property, whatever you want to call this. This is 1/2 D1 sine alpha and then you would distribute that across QT and AQ. So QT plus AQ. But what is QT plus AQ? It turns out that's just the other diagonal, right? We have QT and we have AQ. AQ, QT, AT, D2. Hello? And so this actually simplifies out to 1/2 D1 D2 sine of alpha. All right, great. Now I will leave this as an exercise to you, the viewer. If alpha is a right angle, measure pi halves, then you know, the way this works, actually this still works out to be the same. It just so happens that sine of pi halves is 1, so you would be able to like sort of make this a bit more of a succinct sort of equation right here. And actually, this is how you would find the area of a kite, which is a special type of quadrilateral. The two adjacent sides pairs, they're congruent to each other. If alpha is greater than pi halves, though, well, then we could just use beta, and the altitude would end up being on this side, and I'll leave that, of course, up to you to figure out. But basically, in any case, no matter what the measures of these internal angles are, this works. 1/2 of the product of the lengths of the diagonals times the sine of the angle between them. That is the area of the quadrilateral. This works for all quadrilaterals, no matter if it's also a trapezoid. Yeah, there's an easier way to find the area of that, but this works too. This works for squares. This works for parallelograms. This works for kites. This works for no matter what. No matter what shape it is you're looking at. If it has 4 sides, this formula can be used to find its area. And this was, I don't know, I guess hidden from us as we went through school. But I think it's super useful to know and probably should be taught more often. Now, for our purposes, make sure to choose an acute angle. It doesn't actually matter which angle you end up choosing, but in order to make use of as little additional information as possible, we do need to make sure that we choose one that is less than pi halves. If it's greater than pi halves, just choose the opposite one and label it as, like, I don't know, pi minus that angle, and you're still good. You could still find the sine of it, and then just, you know, obviously you would find the measurement of the two diagonals and multiply them together and then have them. Yeah, incredible, isn't it? Well, we are back where we began. Yep, this was the problem that spurred this whole nonsense, and let's take another crack at solving it, but this time we're going to add some known information, namely the area of a quadrilateral is 1/2 times the product of the lengths of the diagonals times the sine of an angle between the diagonals. Again, it doesn't matter which one. Now, please observe how much easier that this known detail makes this problem to solve compared to last time. Compare just the length of the first video to the length of this chapter of this video, all right? So let's make a altitude. Now, the location of this altitude depends on alpha being less than pi halves. If alpha is greater than pi halves, then it's going to land actually outside the triangle, somewhere over here maybe, I don't know. And in that case, in order to minimize the amount of information that we can use, we'll have to take advantage of angle beta right here. So let's just make a little substitution here. If alpha is less than or equal to pi halves, theta equals alpha, and otherwise we're going to set theta equal to beta. And the reason we're doing this will make so much sense once we write this first expression. We have the area of EFG, which we'll call A. That is just the length of the base, so that is EF, 1/2 of that, times the height. The height is just going to be EG times the sine of alpha if alpha is the lower angle, or beta if beta is the lower angle. So of course it will just be the sine of theta, right? And then we'll do our expansion, yada yada yada. EF will be EFA plus EA. And then EG will just be EB plus BG. And then we have sine of theta. Okay, cool. Now we're going to find the area of this quadrilateral right here, but we're actually going to use our new formula here. So then we have A2 equals, and then the length of one diagonal, which is AC, times a half, times the length of the other diagonal, which is D. Oh, that's odd. There's no B here. dB. And then sine of any of the inner angles, theta, alpha, beta, doesn't really matter. We'll just say theta because, you know, either way it works. And then let's expand things outward. AC can be expanded out to AE plus EC. And then DB can be expanded to DE plus EB. Great. And then we have sine theta. Make our substitutions. That is just 1/2 of AF plus AE. And then EB plus BG, sine theta. So we have A2 equals this big expression, which equals A, and then therefore both of them are equal to 1 QED. And that is all we really needed to do. So if we had come pre-equipped with the knowledge that this formula for the area of any quadrilateral works, this problem would have taken a lot less time to solve. We kind of deal with all the cases at once, and the fact that the choice of angle doesn't really matter saves us a lot of time. Now, if you recall at the end of part 1, I did say that this problem illustrates something very important about math and about anything that involves learning. And that is the following. If you were to take a wild guess as to why this formula for the area of a quadrilateral isn't known more widely, why don't they teach it to us right away? It's applicable to every single quadrilateral. It's like a fail-safe in case you don't know anything else to apply to make it a bit easier. Like, why would they not just tell everyone this formula? I think it's because of this. I think it's because the sine of some angle is mentioned in the formula. And if you think about, you know, all the other area formulas, none of them have angles involved, and they sure as hell don't have any trigonometric functions involved. And so, you know, they don't like that. I think early on in your math career, when you're first learning about shapes and the areas of shapes and the perimeters or whatever, the concept of sine is very foreign to you at that time. So they don't want to mention it. But like, think about what we know about sine. All we know is the definition of sine. It's like what sine is. It's not even like anything that we have to prove additionally about sine. It's literally just the definition. And then we use that definition, and all of a sudden we can synthesize this wonderful formula. And so the takeaway is this. Whenever you see a very skilled mathematician solving a problem, they're invoking all these theorems, they're doing all these operations in ways that you might not be able to understand. It's all very intimidating, and it seems like it takes a genius to get to that level of understanding of the material. But actually, the way they got to that point was They learn the fundamentals and they use those fundamentals to build additional knowledge. And that additional knowledge then sort of became just as well known to them as the fundamentals did. And they kept doing that until eventually, they look like experts. They look like, crazy movie mathematicians filling up chalkboards. The fact that this formula is withheld from the curriculum is frankly ridiculous to me. I don't understand what it is that they think people can't handle. Can they not handle defining sine as something and then using that to prove something else? Do they think that people won't understand the difference between a definition and a proof? Do they think that people just get scared when they see letters in math? I really don't know what it is they think people can't handle, but you are better than that. As a viewer of the Jakester897 channel, I know you're capable of more than that. You're capable of more than any curriculum says you are. You just have to stick to your fundamentals, stick to the things you know really well, and build outward from them. You don't want to just be stumbling blind and be given all this information and have no understanding of where it comes from. Now, a lot of people watching this video are probably very, they're math enthusiasts. When I make these videos, I don't make them for math enthusiasts. I make them for anyone who's interested in learning something new. And that's why I boil things down very, very intensely to the bare minimum. It's because I know that you don't need all this expertise. You don't need all this crazy buildup. You don't need a background to really understand the essence of any of these problems that I present on my channel. You just need some curiosity and some motivation and, fundamentally good logic. That's all it takes. I don't care what the school curriculum thinks. If you have that characteristic, you're as good as Einstein to me. But yeah, anyway, that's about it for me. I hope you enjoyed this 2-part video series, and I hope this problem was somewhat interesting to you. Yeah, like, subscribe, do all the things that YouTubers tell you to do. You can also not do them if you really want to. I'm not going to hold it against you, but it helps me out. It's free, and it'll help you get a hold of more of my videos. So win-win for everyone, I suppose. Yeah, thank you, and take care.